In this video, we're going to discuss orbital shapes and energies. Now, in the previous video, we discussed and introduced the quantum model and quantum numbers and how there are ways that we can label solutions from Schrodinger's equation, right? So we can get this insight from the quantum model and be able to use it for some more qualitative purposes, right? So we call those solutions to the quantum model orbitals, right? So really those quantum numbers are ways that we can label our orbitals. And so I want to kind of take this through each principal shell, or at least the first few principal shells, so we can get comfortable using quantum numbers and being able to relate it to their shapes, orientations, and energies. So let's start with the first principal shell, right? So let's start with n equals 1. Right, so in the first principal shell, if we consider the angular momentum quantum number, right, the angular momentum quantum number is restrained to be from an integer value from 0 to n minus 1. So if n is equal to 1, then our angular momentum quantum number can only be 0, right, since n minus 1 in this case would be 0. So you're only going to have this L equals 0 in the first principal shell. And that means that for 0, m sub L would just be 0. So you only have one orientation, right? So what this means is that for our first principal shell, the only orbital that can exist in the first principal shell is the 1s orbital, right? Now let's look at the second principal shell. So if we have n equals 2, right, if we're looking at the principal shell where n is equal to 2, that means that our angular momentum quantum number can take on different values. So since it can go from 0 to n minus 1, in this case, it'll be 0 and 1, right, as our two possible values for our angular momentum quantum number. So this means that in the second principal shell, you can have a 2s orbital and you can have two p orbitals as well. And those p orbitals can actually have different orientations. If we think about L being equal to 1, then m sub L can take on values of -1, 0, and +1, right? Keeping in mind that m sub L, our magnetic quantum number, can take on values from -L to +L. So if L is equal to 1, that means that it can take on values -1, 0, and +1. Right. So let's take a look at what these will look like, what their shapes look like, and orientations. Right. So for the first principal shell, we saw we can only have a 1s orbital. And we see that pictured here. The s orbital has a shape like a sphere. Right. And you can see here that for the first principal shell, we only get a 1s orbital. Now, when we move to the second principal shell, we have more orbitals. Right. We have our 2s and the 2p. Now note that the 2s is actually bigger than the 1s, right? When that principal quantum number increases, the size of that orbital is going to increase, the size and the energy. So this 2s orbital is not only a larger orbital, it's also a higher energy orbital as well. Now the p orbitals have what's known as a nodal plane, where there's no orbital density in a certain region in space. And so it gives it this sort of dumbbell type of shape. And so you can see that here with this 2p orbital. But you'll notice that we actually have 3 different 2p orbitals, right? That's just like we predicted here with the magnetic quantum number. Since we have 3 different orientations, we're going to have 3 different 2p orbitals, right? So each one is lying along a different axis. This notation of 2px means that it's lying along the x-axis. 2py is a p orbital lying along the x-axis, and 2pz is a 2p orbital along the z-axis. But note that they all have the exact same shape. They have the same size. They would also have the same energy. The only thing that's different between these 3 orbitals is their orientation. So each of these 2p orbitals, same shape, same energy, same size. The only thing different is their orientation in 3-dimensional space, and we predict that we'll have 3 of them. I also put d orbitals here. You'll note that you won't get to d orbitals until you get to the third principal subshell. Let's look at that. So for the third shell, if n is equal to 3, right, then the possible values for L that we can have are 0, 1, and 2. So that means that in the third shell, you'll have a 3s, a 3p, and 3d subshells, right? Now, when we look at M sub L, when L is equal to 2, we're going to have 5 different possible orientations. We're going to have -2, -1, 0, +1, and +2, right? So that gives us 5 different orientations for d orbitals. And you can see that reflected here in the d orbital pictures, right? We actually have 5 different d orbitals. So d orbitals kind of look like p orbitals, except it's like 2 of them superimposed on each other, right? So you end up with this like double dumbbell type of shape, and they all sit in a single plane, these double dumbbells. And so you get 4 that look like that, and then the what is known as the DZ squared is a little bit different based on how its planes are arranged. But you get 5 different orientations of the d orbital. All of these would have the same energy, they have similar shape, but the only thing that's different here is the orientation in 3-dimensional space. You can see this one is lying in the YZ plane. That's where this orientation DYZ comes from. This one's lying in the XZ plane, so that's where this notation DXZ comes from, et cetera, right? So, so we can get our shape and orientation from this notation that comes from the quantum model. Okay, now what we can do is take this notation that we've built up for these orbitals from the quantum numbers, right? And use this to build up electron configurations for all of the electrons in a given atom. So let's see what that's going to look like, right? So basically what I've set up here is a table, right? So on the left side, we have a few different atoms. And on the right side, what we have is the electron configuration. So I've put lines here to denote each orbital, and we're going to build up electron configurations to represent the electrons in each of these atoms using this table. And in order to understand how we're building up these electron configurations, there's 3 principles that you're going to have to be familiar with. One is the Aufbau principle, the other is the Pauli exclusion principle, and the last one is Hund's rule. And I'm going to talk about each one as they come up. So first, let's talk about hydrogen. So hydrogen is going to be the easiest case because it only has 1 electron. So we only have to worry about placing 1 electron in its proper orbital. Now, when you think about these atoms, their electron configuration, they're going to want to be in the lowest energy electron configuration possible, right? So for hydrogen, we just have to place that 1 electron in the lowest energy orbital that we can. Based on our conversation about these quantum numbers, the lowest energy orbital is going to be the 1s. So we're going to place that electron in the 1s. So we write out these electron configurations in a written fashion by just putting the number of electrons in that orbital as an exponent. So we'll say that for the hydrogen, its electron configuration is 1s1. And so I'm going to place an electron in the form of an arrow in this table, right? So I'm going to put 1 electron that's pointing up, right? And that's going to be indicative of its spin, right? Its spin quantum number. So it's going to be 1 with plus 1/2. So that's where I'm placing this electron for hydrogen. So now let's talk about helium. Now for helium, this is where the Aufbau principle actually comes into play. What the Aufbau principle tells us is that just like you add protons to atoms to build up their atomic number, you're going to add the electrons in a similar way, but you're going to add the electrons in the lowest energy orbital possible, right? So for helium, its electron configuration would be 1s2. We're going to place that second electron in the 1s orbital with helium. Now, this is also where Pauli's exclusion principle comes into play as well. Each orbital can only hold 2 electrons. However, Pauli's exclusion principle says that if an electron is in the same orbital with another electron, it has to have the opposite spin. So for helium, you're going to have a single electron in the 1s orbital, and then the other electron is going to have the opposite spin. So one is going to be spin up, one is spin down. Taking this to the language of quantum numbers, right? Each of these electrons is going to have a unique set of those 4 quantum numbers, because one's going to have an m sub s quantum number of plus 1/2. The other is going to have an m sub s quantum number of minus 1/2. Okay, so let's go with beryllium. For beryllium, beryllium's going to have 4 electrons total, right? So again, we want to build it up in such a way that this is going to be the lowest energy electron configuration possible. So of course, we're going to want to put 2 of those electrons in the 1s, right? But we still have 2 electrons left. So what we want to do is put it in the next lowest energy orbital. That's going to be the 2s orbital. Right, so we're going to put both of those electrons in the 2s orbital. So that means for beryllium, you're going to have 2 electrons in the 1s, opposite spins, and then 2 electrons in the 2s with opposite spin, right? Okay, so for boron, boron has 5 electrons, right? So kind of similar to beryllium, we want to put the first 4 in these first 2 s orbitals, right? The 1s and the 2s. The third electron is going to go in the 2p orbital. So it'll have a single electron in the 2p orbital. So you end up with the following configuration, right? Paired electrons in the 1s and 2s, and then you'll have a lone electron here in the 2p. Now for carbon, very similar, right? Build up 1s2, 2s2, and then we'll place the other 2 in the 2p, right? It has a total of 6 electrons. So we've placed those 6 electrons in the lowest energy orbitals possible. Now, this is where Hund's rule comes into play, right? So we know that for the first 4, they're going to look very similar to boron and beryllium. And we know that one of these electrons is going to go into the 2p. Well, we know that both of them are going to be in the 2p, but we have one that's in a single 2p orbital. The question is, do we pair another electron in this orbital, or do we place the electron in another different orbital? Well, what Hund's rule tells us is that the lowest energy electron configuration is going to be the one that has the highest number of unpaired electrons. So, according to Hund's rule, this electron is going to go in another 2p orbital all by itself, right? Rather than crowding with this electron, it's going to go in an orbital all by itself, and that's going to be the lowest energy configuration. Okay, so that's those 3 rules and principles you're going to want to be familiar with, and this is how we use this orbital notation that we get from the quantum numbers in order to build up electron configurations for multi-electron atoms.